In this video, we will be looking how to find the max depth of a binary tree, building solution in JavaScript while also computing the time complexity and space complexity of a solution. Before jumping into the solution aspect, let us first try to understand the problem statement. As an input, we will be given a binary tree. Let's say, for example, this one. We will be having 3, 9 on the left side, 20 on the right side, then 20 has 15 on the left side and 7 on the right side. Let's compute the depth of this binary tree. I will start from the root node, which is this one. I will say at this level of the node that I have with me, the depth is going to be 1. So if I just consider one level, it's at this point depth is 1. Then I go to the next level. On the left side, I will try to find what is going to be the depth now. At this level, I also have a depth counter. So at this level, I also see the depth is 1. So if I say this one plus this one, when I reach here, the depth is going to be 2. Now, I don't have any child nodes here. So let's move on to the right side now. On the right side, I have 20. So let's say I consider this level. So up to this level, the depth is going to be this depth plus this depth, which is going to be 2. Next, I go on the left side of my node that I have here. I also consider this as part of my depth. So I will say, okay, consider this one also. Now, at this point, what is going to be the depth? Depth is going to be this level depth plus the previous level depth plus the previous level, which is going to be 3. So in this case, I find 3 to be the depth so far. Then I see on the left side there is nothing on the right side also. I move on to the right side. I also consider this depth. So at this point I can say that the depth up to the node 7 is going to be depth here plus the previous, which is going to be 3. And the tree ends here and the maximum depth we found so far is 3. So we can say the depth of this binary tree is going to be 3. And that's pretty much it, the logic aspect which is involved here. We will just keep on doing this recursively until we have a node that we can go to. And if you don't have any node you can go to, so let's say you are here and you cannot go anywhere from this, we will just return from here and we will say, okay, there is nothing more to add to it. And whatever the final length that is computed, which is going to be level 1 plus level 2 plus level 3, at each level we just keep on adding this depth that we encounter. And this depth we can compute in terms of code something like this. So we will say we are going to go in a recursive manner, and at each level, so if you have a root node, the depth we will be considering at the root node. So let's say the depth is going to be 1. For every level the depth gets added to the previous value of a depth. So I will say return the current level's value to be added into the depth plus the maximum on the left side or the right side of your current node. And to do that, we will go in a recursive fashion. So we will just say math.max, because let's reiterate what is the problem statement. We have to find the max depth of the binary tree, not just any depth. So to do that, we will just to the current level add the max depth from the left subtree or the left or the right subtree. And to do that, we will just say max depth for root dot left and max depth of root dot right. So from both these values, whichever is going to be the maximum depth. So in this case, on the left side, the depth was at this point, which is here, which was 1. So we said 1 plus 1. So if we had gone from that side, the depth will have been 2. At this level, what is going to be the depth? So we have 1 here, and then you go from here to here also. So when you reach this level, the depth is going to be this plus its children's depth, which is going to be 2. So when you're here, the depth is 2. And the max from this and this is going to be 2. So we will say the depth is going to be 3 that gets returned to us. And that's why we use this max counter. And if you don't have any nodes that you can traverse, we will just say return 0. And when we will return 0, if there is no root, then you just return 0 that you try to see whether something is there in the left subtree or the right subtree by doing this recursive calls. And that's pretty much it in terms of the implementation that we have here. Now, in terms of the time complexity that is going to be involved here, that is going to be big O of n. Why big O of n? Because if you have, let's say, in the worst case, it's a unbalanced tree, then we will visit all the nodes that are existing at the binary tree that we have received. So that's why visiting all the nodes will give you a time complexity of big O of n, because we are going in a recursive fashion. And in terms of the space complexity that is going to be involved here, that is also going to be big O of n. Why big O of n? Because we will be going in a recursive call, and in the worst case you will visit all the nodes when you try to make this left and right calls. So that's why the space complexity is also going to be big of n, because it's going to occupy space in the call stack, and that's why for each node one call is going to be added. That's why it is big of n. And that's pretty much it in terms of implementation. Thank you for watching. Please like and subscribe.